symplectic condition. Symplectic condition, so we have two methods, and then we also discuss together if this condition is satisfied, then that means it exists the generating function. Okay. Alright, so this is your homework. Alright, so today we are going to introduce another method. Transformation. Okay. Remember here, when we initially discussed how to make the canonical transformation from the old canonical variable to the new one, which are also canonical variables, we introduced generating function f. So we have introduced 4 types, type 1, type 2, type 3, and 4 type, or a mixture of this. Then after we have the generating function, we do the total derivative, time derivative of this generating function. Then substitute into this canonical transformation condition. When we substitute into this way, we will find that some of these, the general velocities, the q dot, q dot, the capital Q dot speed equal coefficient. So from there, we can find the partial derivative of the f function. Since there's a different type, so I didn't write down here. But just something or qg or qg or capital, depending on which type, right? So we got this. And the reason the useful information from here is from here we can find this transformation equation between new and old and new. Once we have this, so what we have to do, we are going to substitute this into the Hamiltonian and the generating function. Since Hamiltonian is function of old canonical variable, right? When we substitute into here, so the Hamiltonian is converted to as a function of new canonical variables. Then the function fi, generating function is half, right? Mixture of the old and new. So the old one also you need this. Then we all substitute here, so finally we can find k is equal to h plus partial f and partial t. Remember, from here reduced to here. Then once we have the new Hamiltonian, we are going to apply the Hamilton's equation to solve the dynamics of new canonical variables, qj dot, pj dot. When we solve the qj and pj as function time, then what we have to go back to here, because this is our final result, right? We are going to substitute the capital Q, J, capital Pj into the lower and old one, Qj, Pj, and then we can find the final, this solution. So that is this scheme. But now, as we say that the difficulty or challenge is how to find this generating function. So another way is today we are going to introduce a symplectic method is if we know the transformation. So here, instead of come to here, we already know here. We know there is a new set of variable, but we do not know it is a canonical variable or not. So we are going to prove if these new variables are canonical variables, then we just go to here. So that is the method we are going to introduce. In this case, this is in the matrix representation. That means, it doesn't mean that something changed, just means since you see the variables G from 1 to n, right? So we put all into the matrix. Remember we previously introduced eta, right? Is Q1, Qn, P1, Pn, right? This is a 2n by 1 column matrix. This is we introduced before, right? And if you remember, okay, and you remember we also discussed, so the total time derivative of this canonical variable, that is dq1 dot, that is q1 dot, q1 dot, P1 dot, Pn dot, right? And this one, according to the Hamilton's equation motion, follow this. So that is partial H, partial P1, partial H, partial Pn, partial H, partial negative partial H, partial Q1, negative partial H, partial Qn, and this is, if you remember, we introduced J, right? So this is a matrix representation of the Hamilton's equation motion. Remember, I introduced this before. Now we are going to use, I think in chapter 8, right? So, and this one is this, and you know, remember the J, right? The minus J is 0, n by n matrix, and this is a 1, n by n matrix, and this is a minus 5, n by n matrix, and 0, n by n matrix, 2n by 2n matrix. Remember this. Okay, so now we start on here. That is, we suppose this is for the, this is a canonical variables, right? Canonical variables, which we already know. So now for the new one, now we are going to, okay, let me use this. We are going to transform to the new variables. And now we are going to ask ourselves the canonical variables, canonical transformations. So how to do that first? Let's know. Also define the column matrix. So here the new variables Qj must be function of old one, right? In general, and Pj. But the question is, they can now make out variable. This is a question, so we are going to prove. So how to prove that? We prefer to use matrix since there's a lot of variables here. We make this a matrix. Now we are going to consider this case. Restrict. This restrict is satisfied in most cases. Restriction is that the partial Qj does not depend on time explicitly. So here, I'm going to, that means Qj is only function of the old canonical variables, no time, but implies implicitly because Qj, Pj as function time. So, but not that does not depend on time explicitly. Then we have this case we are going to consider apply the symplectic approach. Okay, so that is the case we are going to consider. Then we are going to follow the same thing. We are going to use matrix. Instead, this is a eta, right? Now, for all the canonical variables, is a matrix, but we are going to use the zeta as a new canonical variable matrix. So that is capital Q1, Qn, P1, Pn. Again, it's also 2n by 1 column matrix. We just make the matrix, right? So that you see, this one is old canonical variables. This is built by new canonical variables. Column matrix, the column. So we are going to see the relation between these two, right? Okay, so now here, since these new variables are a function of old one, right? So actually that is a Q1, which is a function of Qj, Pj, right? So I remove time because we just consider this case. Each one are function of all canonical variables. So I can write this way, if you agree. Zeta is a function of eta, right? These are all just a matrix representation. Okay. Now, if this is we define, then let's look at this time, total time derivative of this zeta. Okay, let's consider this first. One of them, right? Let's consider one of them. So I use I. That is the reason why I use I, because you will see here. One of them is the function of old canonical variable Qg and Pg, right? So we do the total time derivative to the summation partial zeta I is Qg dot, right? Wait a minute, not just zeta, because all these functions are both, right? Partial zeta G, zeta G, right? Okay, so if this is one of these elements, then if let me just use the matrix. So here, this is a column matrix of all the total time derivative equal to 1 dot, right? Since I use zeta, this is just here, right? So that is 2 and dot, right? Okay, that equal to, you can see here, for each one, that is I, right? In this term. And from this term, you can see this is nothing but this summation for all the row with the column, right? So that is the square, bigger space, and zeta 1 dot, J dot, zeta 2 dot. And inside here, this is a partial zeta 1, partial eta 1, partial zeta 1, partial eta 2n, right? And do the same thing. Partial zeta 2n, partial eta 1, partial zeta 2n, partial eta 2n. So we introduce a square matrix. Yes, I'm going to say this matrix, I'm going to introduce M, and that one is stop. Okay. So now the M is a new square matrix we introduce. Now we give for the name here. And that is the relation between the old and new variables. We call it Jacob. The M is Jacobian matrix. So M, the matrix element, okay, Mij, the S column and just S row to column is partial zeta I, partial eta G. Is one of it, right? So that is the, we introduce this square matrix. And once we introduce this square matrix, so that I say that we have this relation between this old and new one, the old dynamics and the new dynamics. So this is a total time derivative of the new variable is equal to this Jacobi matrix multiply the total time derivative of the old canonical variable. Here we do not know it's canonical variable or not, but this one is canonical variable. Okay, so now we are going to see the relation here. Or get this condition. If the new one are canonical variables, that condition. So next one is condition. Canonical transformation. From eta to zeta. Right? So how to do that? Okay, since we know the condition here, let's first we know the relation, right? Zeta dot is m eta dot. Second one, since eta are kinetic variables, so eta follow this because this is kinetic variables. So second information we have, zeta dot is G partial H partial zeta, right? Second relation. Okay, third one. Let's look this one. So partial H, this is so one of them, right? Let's consider if I use R. That is this term, one of this column matrix, if one of them ith row, that's equal to, since Hamiltonian is function zeta, but if we look the relation between this one, if the zeta is function eta, then inverse, right? Eta also function zeta. So I can say here, summation of J partial H partial zeta, J partial zeta, J and partial eta I. Okay, right? That is just because it's a function of all is zeta. So what that means, this is also kind of a column matrix, right? So that means this is each one of the matrix elements. Therefore, we can easily to find this partial H, partial eta, this column matrix, so equal to, again, here, this one, you see, this I introduced the Jacobian matrix is partial zeta I, partial eta J. This is just reverse. So that is a transport, right? So now let me first get here. So partial zeta 1 partial eta here, summation for all this partial eta 1, right? And partial zeta 2n partial eta 1. And to the end, partial zeta 2n partial eta 1, partial eta 1. Partial zeta 1, partial eta 2n, partial zeta 2n, partial. Here, this is the partial H, partial eta 1, partial H, partial eta I, and partial H, partial eta 2n. Sorry. So, what is this? If you look this one, this is the row is fixed zeta, and change the denominator, right? That is this row, and the column is fixed eta, but change is zeta. This one just opposite, right? So this is nothing but we just do the transport. So that's equal to n transport partial H partial. Wait a minute, I think I did something wrong. This is a zeta, not eta. This one, right? Partial H, partial eta 1, 1. Partial H, partial zeta 2a. Okay, so we have 1, 2, 3. Now we can use this relation to find whether the new variables are canonical variables, that if they satisfy the Hamilton's equation of motion, then they are canonical variables, right? So now let's look from here. Okay, from the first one. So now total time derivative of zeta equal to m total time derivative of eta and n. So now eta dot is this one. The second one is j partial h partial eta, right? Then I keep m j here. This one is this one. Is n transport partial h partial zeta. So what does this mean? This means the new variables total time derivative equal to this the product is 3 square metric multiply the time derivative of multiply the partial derivative of Hamiltonian with respect to new kinetic variables. So compare with, let me just use this. Compare with this is this is a kinetic variables. If kinetic variable follow this, so if we ask this one also follow this, so that must be equal to if canonical variables, right? So this means, okay, this means if the new variables are canonical variables satisfy this equation. So now this one we know this relation, so now that means the condition, what is condition? The condition means this 3, the product with 3 matrix is equal to J, right? If this product equal to J, so then this one equal to here. That makes sense? So this is a condition. This we call symplectic condition. So now we come back to from the beginning of the question. The initial question is we have the old kinetic variables. Then we make transformation to the new variables, but we are going to check whether the new variable or this transformation are canonical transformation or not. That means we need to check satisfy the condition or not. So this is the means. If we found this satisfied, that means the new variables are canonical variables. So this became very simple. You know the M, right? M's here. So when we know this 2, so we can find M matrix and go build up the matrix of M transport, and we know the J, right? J is somewhere, and you know J, right? So then you just do that. That is the homework, the first one, the first question you need to do. If you there's a relation between this and this, we are going to double check whether it's satisfied. So that is the simple condition to prove this transformation is canonical transformation. This condition, there are some others, and to save time, I think that is very simple, so you can do yourself. Another one is J equal to here and transfer inverse. That is simple, right? You just multiply the right hand side and transfer inverse, so this is become 1, and this is this term, and this is J. Or Jm equal to m transport inverse J. So, or m transport J and m equal to J. So they all are fine. So which one you prefer is up to you. They are equivalent. Okay, so this is, let me see, we can do one example, see how we apply. Yes.
For unfilled, are they a unitary transformation method?
Yes, actually they are unitary. This later we are going to discuss the property of this one. Yes, they are unitary transformation, yes. Okay, now let's do one example, see how we can apply this condition. Example, let's give the genetic function. Since we know, if we know the genetic function, we can transfer the old to the new one, which must be canonical variables. Right, so we use that result and double check if they are canonical variables, is we satisfy this, right? So let's consider 2D system. We have a mixture of, for 2D system, we have a mixture of genetic function. Let's say just if genetic function is a mixture of F1, I think I discussed, I will do this type of example before, right? F2, so F1 is interchange, so that means Q1, Q2, Q2, P2 interchange with capital Q2 and capital P2. Q1 and P1 is identical. That is F2 type. So if we have F2 type, we must have this one. Right? Remember that is Jenkins function. And here, in that time I didn't give details of this. Now here I give details. Very simple. This is a product of Q2 capital Q2. So that is this one. And F2 is also simply the product of Q1, Q1. So that is Jenkins function. So with this Jenkins function, we can find total time derivative, right? Total time derivative. df dt, right? So df dt. So here you see this is a function of mixture. You see the variables here, Q1, Q2, this old one, right? And the new one, oh sorry, this is the one. The new one is capital Q1, capital Q2, and capital P1, right? That is this mixture. So the df dt, total time dt, first to this one is Q2 dot, capital Q2 and capital Q2 dot, capital Q2, right? This total time dt, and this one is Q1 dot, capital P1 and Q1, capital P1 dot, and this one is minus capital Q1 dot, capital P1 minus Q1, capital P1 dot. That is total time dt. Then we are going to substitute this into, this is two-dimensional of this, into Q1 dot, P1 plus Q2 dot, P2 minus H equal to capital Q1 dot, capital P1 plus capital Q2 dot, capital P2 minus K, and plus that, and just that here. Is equal. So you can see here this this one, this one cancel, right? So then the remaining part you can see is Q1. So we have equal is P1 equal to capital P1, right? Yeah. Q2 dot, this one is P2 equal to capital Q2. Q2, this is not Q2, sorry. This one, yeah. Yes, P2, yes, okay, P2. Then we have, so these two finish. This one finish. Then now I go to here, capital Q2. Capital Q2 is this one, right? So capital Q2 gives us Q2 is minus P2, right? This one. And the last one we have Q1, this one, and this one. So Q1 is capital Q1. Okay, so we have this relation, and this relation gives us what? Gives us this transformation equation between old and new, right? So we can, with this relation, we can find this map to n matrix element. Okay, so now Mij, right? Partial zeta I, partial beta j. Okay. And then let's do this. We just do this. So the matrix, because it's two-dimensional, right? 4x4 matrix, right? So first one is this equal to 1. It's capital 1, capital Q1, right? Capital Q1 is this one. Capital Q1 also functions is old Q1. So capital Q1, capital Q1 partial Q1, right? And capital Q1, Q2, right? So here, this one is 1, and other are 0, right? There's no function of other variables. And do the same thing here. So then the second one is capital Q2, right? You just follow this new, the order is from Q1 to P. Capital Q2 here, then capital Q2 comes to Q1, and go to here. So capital Q2 is here. Does not relate to Q1. So that will be 0. And Q2 also 0. And then there's a P1, 0, only the last one, right? Okay, similar things. Then there's a capital P1, capital Q1, so that is P1. P1 is this one. Only a function of P1, lower P1. The other are 0, so that's the third one, right? You may ask, so this is the Q1, Q2, P1, Q2. The order. Capital Q1, capital Q2, capital P1, Q2. That is order, right? So now you see this one, P1 is only the third one. And then the last one, P2. P2 is here, negative, -1. This is how you build up M. So when you have M and check M, J, M transport equal to 1. And we have, so that is the goal, right? So then you just, you have this, you can do this transport very easily, right? So M transport, when you have M, you just do the transport, so that is, row became column became row, right? So that is this one, 1, 0, 0, 0. The second one is 0, 0, 0, 1. Third one is 0, 0, 1, 0. And then number 4 is 0, -1, 0, 0. Yes. Okay, then you just check, and then we can substitute this. We found yes, and this is for this one. You can do it, check yourself very easy. So I save time, and that means yes. It is satisfy this condition means this transformation is canonical transformation, and we know because we have generated function, definitely they are canonical transformation. So double check. And in other case, like homework, we do not know whether the relation between old and new are canonical variable, canonical transformation or not. You're going to check this. If yes, and you say okay, that's canonical variable, so you can do that. Now, this case, remember I assume the restriction is partial Q J partial Q equal to 0, right? That is restriction. Now we release this restriction. So if does not depend on time explicitly, how about this symplectic approach works or not? Right, so that is question. We can still use this condition to check whether they are canonical transformation or not, and the answer actually is yes. So that logically is like this. So if the new variable zeta is a function of old one and time here, like this, right? Also depend on time explicitly. And this one is canonical transformation from the, so suppose we know, we follow this. That is canonical transformation. We are going to double check whether this works, right? So in this case, then we definitely know if this at any time this transformation between the new and the old are canonical transformation, so the T this one is also canonical transformation. because canonical transformation gives us a relation between the formula or relation between the old and new one. So if the time change, we just there's a change at the t equal to 0, this relation should be kept at the t equal to any time, right? So now if if we know this from t naught to t, it still is canonical transformation, then we can prove that this symplectic transformation condition, symplectic, holds true. Now this we are going to give the idea. So if we have the canonical variable are dependent, or the variable dependent on time, we have the transformation. However, in the transformation are canonical transformation, so even at time, we can still use this symplectic condition to check, or this symplectic condition also satisfied. To prove that, so that is key, we are going to prove here. To prove this one, let's consider infinite. Yeah, let's consider the infinitesimal transformation. So just as a simple notation, ICT. That means if from this data from t naught move to this time t, it is follow this infinitesimal canonical transformation. If that is satisfied, then we are going to find that this one still holds true for the time. So how to prove that, or prove or check? Okay, let's see, check is better. Check. Okay. Since we consider infinitesimal change, so that is the new variable actually is start from the origin plus infinitesimal change of this. Okay, so that is the new one. Actually, it's just take the various infinitesimal canonical transformation from the old one. So that is the old one plus the infinitesimal part, right? That is considered start from here. That is this. Okay. Then now we are going to see whether this are canonical transformation or whether this symplectic condition works or not. Now let's consider like this. Here, the new one, this new one, right? This old one. So the difference is only small difference. That means this transformation is which type? Identical, right? Remember, F2 type is that the old the coordinates is still a general coordinate, still become a new general coordinate. Old canonical conjugate momentum is still new one. So because this, so we need this identical transformation. For this case, infinitesimal change. So that's be a kind of identical transformation. If identical transformation, that is F2 type. You can say F3 type, yes. You can also use F3 type, but let's just use F2 type as example, right? So if F2 type we know this this partial derivative is Pj is partial F2 partial Qj, right? And capital Pj. F2 type is F2 type is QP, right? So the capital Q is a capital Q. Right, F2 type is F2 function of Q, G, P, G, right? That is mixture of this old kinetic coordinates and the new kinetic momentum. So that is this one, and this one should be partial dt plus. Okay. So now that is this one. And then now from here. So this is for the P part for this. I haven't clicked this. Okay. So this F2 type is, since I'm going to use the identical, right? Identical is simply just a product of QG and PG, right? G. But I need to have an infinitesimal change, so I need to add another infinitesimal term. Here, it does not depend on time. So the time dependent part is come to this one. Here, this one is infinitesimal parameter. Like, if we want to change is a spartan time, is like t, or displacement like q, or a change of the momentum. So that is the infinitesimal change, a parameter that make this transformation. And this G we call the generator. Later we'll see this very important. So that's just, this is a function, we call here generator function. Okay, which is, this one requires this any differential function. There's no any okay, now let's come to here. If F2 is this way, so now let's do the partial F2 is QG, that is this one, right? So that give us PG, factor PG, and this one is plus epsilon partial G, partial PG, right? Okay. And from here, so we have a capital PG is lower PG minus epsilon partial G partial PG. We need this one substitute. Right, so that is the first one. Second one, this one is now capital PG, so that is QG, partial F2 partial capital PG, this one, and plus epsilon partial G partial PG, right? Okay, so now this one is for QG, this be lower QG plus QG, right? According to this. And from here, that also equal to QG plus epsilon partial G partial PG. So that is the QG. And the PG is PG plus delta PG is here PG minus epsilon partial G partial QG. We're going to find the delta eta and find this kind of infinitesimal canonical transformation can be proved. It is set by this condition. So here, but this one, we see this one is partial G partial capital QG. So now we are going to look at this one. Because here, partial G partial capital PG and partial G partial lower PG, partial lower PG, partial capital PG. And since we have this infinitesimal change this difference, this is small, so we can approximately this one is approximately 1. So this the lower PGA and the capital PGA's difference is infinitesimal small. So we have partial capital partial G partial capital PGA is partial G partial lower PGA. So now we can rewrite here QG plus epsilon partial P partial PG. Okay, now we have this matrix is a polar matrix. Now the polar matrix, which is Q1, Qn, P1, Pn, right? And delta Q. Okay, let me write down here. Delta Q is this one. Is epsilon partial G partial P, right? P1. Epsilon partial G partial Pn. And then the delta P is negative. So that's the negative epsilon partial G partial Q1, negative epsilon partial G partial Qn. If I write down here, I think you will agree. You see, just reverse and this makes sense. This is the role played by J, right? Okay, so now you see we have a matrix relation with this. So now we are going to see okay. So the mu zeta is mod eta plus delta eta, which is this matrix representation of this. Then let's try to see if we satisfy this symbolic. So now let's use m. M is now is function time, since this is dependent on this the transformation is implied with this time, also includes time dependent, right? So that is dependent on time. So now here, that is equal to partial zeta plus delta, zeta partial zeta. The first one is the unity of the matrix, right? The second one, partial epsilon G, partial G, partial eta, partial eta, right? So that is second order derivative. Here the J I can take outside because it is just a constant. So only the partial derivative of the G function. Okay, that is M. Now we are going to see here, because the second order derivative of this is the matrix elements in partial square G, partial zeta I, partial zeta J equal to the second order derivative of the partial, first partial I, zeta I, so they are interchanged. So what does it mean? This second order derivative is here partial its transport is equal to itself. We need this. Okay. Then now let's double check whether it is this condition satisfy the symplectic condition or not. Let's look this term. So check this one. M is this, right? Yes, M. Okay, M is here, right? That's M. Is 1 plus epsilon G partial square G partial square. G. Now, M is transport. The unit matrix transport itself, right? That's J. So this okay. I didn't do the transport. Okay, so now if I just write here, so that is partial square. Here, what is important? If I take the transport, so that this product of a square matrix is another one. So when we do the transport, the positions change, right? So that is partial square G transport and G transport. You see, this is M. This is M transport. So the transport means if A, B, transport is B, A, right? So that is check, okay. Then here, we keep continue here, since we need another step. This one is minus, remember? The J transport equal to minus J because this relation. So that is epsilon, and this equal here. So I change to so here we use the information property of J and property of G. Second order partial derivative of G is transport equal to itself, and the transport J is equal to negative J. So now we can do here. The first one still is J, right? This multiplies, so that is J, right? First term. And this one is this one, so that is first and minus J epsilon. Right? This term multiply and this term. So, and then the next one is this one multiply. So that is epsilon there, J partial square square J. And the last one is this, right? So last one is epsilon square J partial G square partial eta square J and partial square. Okay. This term we can ignore because this is epsilon is infinitesimal small. And these two terms cancel. So, you see, yes. Even though it is has a time, depend on time explicitly, but we already proved this infinitesimal, so we prove infinitesimal change from zeta t naught to zeta t. This is an infinitesimal canonical transformation because it satisfies this condition, right? So we prove that, and later we will see this the other case. But now, yes. Sorry for this. And the remaining part later, there's some of a property about this transformation. I think that is. First, we have identical transformation. Is coming. Because no transfer, right? That definitely is no transformation. Second one, if A is canonical transformation, then its inverse is canonical transformation. So that means we have a transformation. I just use A to represent this kind of operation, this transformation. So if this is a transformation, means we have a transformation from old to new, which is canonical. So the inverse is also canonical. That is the property of the canonical transformation. Third one, okay. If A and B, there are two canonical transformations, then the product C equal to A, B is also, okay, I don't have a space here, so I just use a simple case CT is canonical transformation. Okay. And 4 is associated, so that A, we first do the canonical transformation of B and C and do A equal to, we first do C and then do the A multiple B. Those are these properties. But I think we will probably will not use those details in this class, so just mention here and you just know that what you want. Okay, now we want to extend our discussion about this symplectic condition and its the role played. In particular, if this is satisfied, it will imply the existence of a generating function f. So, but before the discussion, that properties or advantage, we are going to introduce the Poisson bracket, because that one is very important, and we need that property, the bracket, Poisson bracket, to prove the existence of a generating function if the symplectic condition exists. So now let's. The Poisson bracket is very important. It extends to the quantum mechanics, that is commutator. So, Poisson bracket. And invariant. That the sum of variables will not change under the canonical transformations if Poisson bracket is invariant. That is very important. So now let's first definition. What is the Poisson bracket? So if U is a function of general coordinates, and that we have two functions, which is a function of general coordinates. Okay, then look this partial derivative of partial U with respect to the general coordinates multiplied partial V with respect to our conjugate momentum minus partial U partial conjugate momentum and partial V partial general coordinates. This term. So you see this key is here. The first variable with respect to the partial derivative first half of the general canonical variables. Multiply the second function with the variable with this second canonical variable. Subtract the first function, the partial derivative with respect to the second part of our canonical variables. Multiply the second function of this partial derivative with respect to the first part of the canonical variable. So give a notation. That is the definition. So, and you may say, why we introduce this, and you will see the important play the role here, right? So if we define this one, and now it is the matrix representation, also very important. Since we use that and make the expression simple. Matrix representation. Okay, let's look this up. Because if you have a column as a row, partial U, partial Q1, partial U, partial P1. Okay, multiply J. J is, remember that is n by n, 1, n by n, and minus 1, n by n, 0, n by n. This is a J, right? And the column is partial V, partial Q1, until partial V, partial P1. So let's look at this one. And you will see they are equal to this. That gives us this matrix representation. So because this one equal to, you can see here, this row multiplies column, that gives us the second part, right? And then so, okay, partial U, partial Q1, partial U, partial P1. And here, this column is partial V, partial P1, right? Partial V, partial Q1. After this, okay, the minus here. Right? Because we have a minus. Then you can see this is equal to, right? You see, products. The first half product is this one. And the second half we have next sign here is this one, right? So the Poisson bracket, the matrix representation is like this. Here, the first one is partial U is transport, right? This one is transport by the row, right? And the J, partial V. So this is definition and equivalent to this one. Okay, that is definition. Now we are going to discuss some of a particular Poisson bracket. The first one is what we call the fundamental Poisson bracket. What this means? That means if U, V, U, P. That means the function, we say is arbitrary, right? It's an arbitrary function, but now if the function is nothing but the kinetic variable itself, then what is the Poisson bracket of kinetic variables? Then let's see. Suppose, let's look at this one. U is a Q. Qi, Q, let's use K. This Poisson bracket. Okay, that is by definition is partial Qi transport, right? And partial zeta J partial Qk partial zeta, which is equal to, by definition here, right? Summation J partial Qi partial Qj partial Qk partial Pj, right? Minus partial Qi partial Pj partial Qk partial Qj. Understand here? Okay. Then how much? See here. They are independent, right? So this will be 0. This one is 0, right? So this is 0. And that means the conclusion is the Poisson bracket of the kinetic variables itself always equal to 0. Second one, Q, let me do this one, Qi Pk. Okay, so that is partial Qi tutor, partial eta J, partial Pk, partial eta, which is summation j partial qi partial pj partial pk partial pj minus partial qi partial pj partial pk partial qj. 1, right? Yes. Because here, this is a 1, since when j equal to I, and j equal to, okay, when k equal to j, because so that means here. This one definitely there's a 1, but this one must be j equal to k, right? So that is delta jk. Sorry, delta I, no. Delta I, k. If they are the same, so we definitely have the same j. But this term is 0, right? So second term is 1. But only this term, if I equal to j equal to k, then we have a j definitely there's equal to in the summation. But if I not equal to j, then this one equal to 1, but this one is still 0, right? So that is this one. And similar for others. So let me give you a conclusion. Because if you know this, it's pretty much like this commutator between the position operator and the momentum operator, right? So now, let me summarize. You can do this Pj, Pi, Pk, that's the same thing like this, right? And then this another is Pk, Qk. The last one is, again, this is just opposite, change the position, right? So now I'm going to use matrix. That is the Poisson bracket of this position, kinetic variables. If I use matrix, this matrix is Q1, right, until this Q1, Pn, and then Q, so now let's see. So here all are the Qn, Q1. Here this is the Q1, Qn, right? Yes, and this is the Q1, P1. Here Qn, Qn. And this is Qn, P1. Qn, Pn. Then this part is P1, Q1, P1, Qn, and then Pn, Pn, Q1, Pn, Qn. Here, this is a P1, 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 Pn, Pn, P1, Pn, Pn. All this Poisson bracket make this together as the matrix. That is 2n by 2n matrix, right? Okay. Now you can see there are 3 sub-matrix and have the very similar behavior. So now I'm going to make simple. You see, I'm going to make this. So the first corner here, this one, is about this Q. All the Q, different Q, right? So here, all the Q, the Poisson bracket between Q1, Qk, or Q1, or Qi, Qj, whatever. It's all this Poisson bracket. So I just use this part. I represent by this, all the possible. That's just a notation, right? So this does not mean it's Q. This means Q include all this possible in there. And that one is QP, right? And the bottom one is PQ. And this diagonal term is PP. So you immediately know this equal to what? This must be 0. Here, right? All this, so that is 0, n by n matrix, right? Oh, sorry. N by n matrix, right? This one is unique because only when Qi equal to Pi, other also 0, right? So that's the diagonal pair, is this one. This one change the order, right? The next sign. And the last one also 0. And what is this? It is J. See, that is very important. So now let me give a conclusion here. The fundamental Poisson bracket, that means the Poisson bracket of this kinetic variable actually equal to J. So I have I immediately got this one. And just occupy a few minutes to discuss the properties. So now here, this is the first. Now we are going to the property. The first one. Is environment. So that means this fundamental Poisson bracket is environment under canonical transformation. Because if between these two are canonical transformation, then they are equal. That means whatever the old canonical variable, the Poisson bracket equal to the new canonical variable bracket. That's proof very easily because here, right? So because M is partial zeta, partial eta, M transport is partial zeta transport, partial eta. Okay, so let's take this the Poisson bracket of this new canonical variables. By definition, is partial. Right? This any this one. Right? So that is G partial eta, partial eta. Then here, this one is N, right? Is N transport G, and this is N. Because it's canonical transformation, so not equal to G. Right? So that's all, right? So that I just prove very easily. That means that is good. So we are not worried about the canonical transformation. The Poisson bracket always keep the same relation. And similarly, same for any U and any function. This is for the basic fundamental, right? So now this one equal to partial U transport partial eta G partial V partial transport. And that is also equal to U with the new canonical variables, the Poisson bracket, which is equal to partial U, partial zeta, G, partial V, partial zeta. That is, okay, I think I can prove maybe on Thursday. Very easily, if you can prove yourself. Try to prove yourself. Okay, yes, let's stop here and we will discuss the important, after we introduce the Poisson bracket, there's a lot of important issues. We can have this idea how the dynamics equation motion will also unchain or invert under this canonical transformation.
Shall we finish chapter 10 also?
Definitely chapter 10 we can, chapter 9, I hope chapter 9 I'm not sure we can finish or not by this semester. But if yes, the last day, maybe I really want to introduce the first part of chapter 10, since our goal is transfer to this canonical transformation and make this all these canonical variables are cyclic, right? Then we can solve this consequential motion. But let's see if then I may ask you if you prefer. We have another day. Reading day is Tuesday, December 6th. If you prefer, we can discuss something or discuss homework or discuss some of problem. Yes. So let's see. Yeah. I made some of part I may just judge. If not just important, I will like Lagrange cooperative, I will not deal with.
I think we have only 3 classes.
Yeah, we have 1, 2, 4. Next Tuesday we still have
Next
one.
Tuesday, yeah.
Yeah, so
Next
Thursday, next Tuesday, and then after Saturday we have 2 classes.
December 1 is the last class.
December 1st is the Thursday. Last class.
For the very last part.
Doing this?
Yeah. You know, I got there. Oh, okay. Every now.
Yeah, so like B can be like there's a singular value decompensation like U and
That is not. We didn't say that. We say the complete the transformations between the canonical variables, not functions.
Yeah. I don't like to rely on that, after not much trouble. Thank you.
All right.
Did it used to be a second semester for classical?
So far, no. Yeah. I'm not sure. At least I already teach this how many years? 2012. So 10 years. 10 years now. No any second or serious class.
That's a shame.
Yeah, I wish to have the chance.
See you tomorrow.
See you. Hi. Are you okay, or we can discuss if you want to discuss?
No,
It works now? It's
yeah.
clear?
Yeah, it works.
Yeah, I think just since we consider 2 particles, when you consider at least 1 particle somewhere, but you also need answer for the second particle.
Mm-hmm.
So that is the.
I actually have my assignment for you. It's my assignment from yesterday.
It's, yeah, that is each individual you have a. The energy is okay. The wave function, total wave function product, right? Yes? Yes. Okay, that's it. Yeah.
Yeah.
That is.
Oh no, I'm turning that into you, but
Ah, you,
yeah.
okay.
That's it. That's it.
That's it. Okay. Okay.